Thank you for reminding me. Okay, so yeah, never fear if you see Canvas marking an assignment late. If I'm not mistaken, I don't have control over that in it to the following extent. I set a due date in order to keep us on track, right? So I say, hey, we have this due on thus and such a date, but then the deadline for an assessment is typically later. So the only way I believe for me to avoid that late notification that you get is if I change the due date. But otherwise, Canvas just does it. It's not anything that I pay attention to. So don't stress over that. Thank you for bringing that to my attention. The other thing that, and I'm not sure if it's happening in your class. This is the only section of Phil 9 I have, so I'm gonna say something that is meant to be that might not compare with other classes, but some folks are saying, "Hey, Mia, my lowest score is being dropped when I haven't finished the series of assessments." And I said, "Yeah, I think that Canvas, in my view, has some and other learning platforms do the same, have some settings that I think are a little bit wonky in that if I say, okay, within thus and such a category, I set Canvas to drop the lowest score, right, within the category, even if you haven't finished the assessments within a category, your current lowest score gets dropped, and sometimes that throws people off. So, again, anytime anything looks wonky, let me know, and I will sort it out, or I'll check into it. Okay, so where were we? We were deep into what I'm going to call the world of truth functionality. And so one way we can think about this study is as follows. We can think about determining possible truth values of a given sentence, or sorry, let me back out of that, of a given sentence. So possible truth values of a given sentence when that sentence involves at least one Boolean connective. So the way that we determine possible truth values is with a truth table. So you think about your truth table as kind of this machine that grinds out truth values. Well, how does it do that? Well, you input your atomic or simple sentence possible truth values, and then whether if you have, sorry, rephrase, and then if you have multiple operators, you begin by determining the values of the sub operator or operators in order of increasing scope, right? And then the main or driving or governing operators' values are determined last. So what you end up with is a set of rows or lines in a truth table that tell you the conditions under which this sentence is true or false. We saw that we can assess those, that any given individual sentence as contingent. That is, could be true, could be false, depends on the conditions, right? But again, going back to Zeba's clarification in the version of the system that we're learning, a contingent sentence is going to be true on at least one row, false on at least one row. What I was doing originally was assuming a distinction between contingently true or contingently false, but we will just say with our textbook contingent. So you can assess a sentence in terms of three concepts: contingent, logically true. On a truth table, a logically true sentence is a tautology, or logically false. On a truth table, we're talking about a tautological falsity or a taut falsity. We then said, okay, we can do what we did for an individual sentence, but now we can do the same for multiple sentences. So let's say we want to compare two sentences with each other to see if they are equivalent or truth table equivalent or tautologically equivalent. What we are saying there is that on every row of the truth table, in the column under the main operator, if there's more than one operator, the values are identical, right? We can also say that equivalent sentences show us that we can infer one from the other. We can go back and forth. So there we press on using a truth table to determine validity. Where we're looking at more than two sentences with an eye toward just one of those sentences being the conclusion, we do the same thing that we did for an individual sentence. We do it for all the sentences in the argument in terms of churning out the possible truth values, right? And then we look across row by row to see whether or not on those rows, assuming there are some, where the conclusion is false, the premises are all true. If the premises are all true on the same row that the conclusion is false, the argument is invalid, right? That's just the definition of an invalid argument. So we talked a bit about the fact that the truth table has a very strict and relatively speaking, narrow scope in terms of what it can do. But it's a really robust tool, right? So if we know that we're dealing with what are known as truth functional sentences, right? We're talking initially about Boole in chapter, what the heck chapter is it? Why am I blank? Where are we? Hold on. Yeah, when we move into the next set of connectives, that's what, chapter 16, 17? Yeah, for propositional logic, we're sort of adding on to our existing knowledge right now that's restricted to negation, conjunction, disjunction. We'll add two more connectives, and one of the things that we'll want to be able to do then is say, look, whenever we've got a sentence that is governed by one of five operators, we can throw that sentence into a truth table, grind out our truth values, and see the possible truth values of that particular sentence, and do the same for equivalences and validity. Okay, so it's a powerful tool, but a pretty restricted tool. And one of the things I like about doing this kind of work is we say, okay, among other things, I see that when we're talking about truth in the realm of logic, we're talking about the logical structure of a statement, right? Here in the realm of the truth table, it's the logical structure of a statement as determined by the atomic or simple sentences and the connectives that compound them. Okay, so I hope all that makes sense. As usual, if you have any questions, problems, confusions, just pipe up, right? Either, so I've got the chat window open. You can either say, send me a chat, Mia, what did you just say? Or I don't understand what you've just written or whatever, or just speak up if you're willing to do that. So let me go ahead and get our whiteboard going. I also hope that if you have questions, problems, confusions about any one of the exercises in the textbook or any of the exercises in our quizzes and exams, bring those to the table. We can always talk about those to clarify any part of the confusion that you are having. All right, so let's do this. Before moving into using the truth definitions of our operators as the foundation for rules that we will use to prove or establish or demonstrate the conclusion of a valid argument, right? Let's talk a little bit more about how the truth table displays validity, okay? So as a reminder, so let's just do a quick review of truth table or tables for assessing tautologically equivalent statements and valid arguments. Okay, so we know that two or more statements are, and I'm just going to put in parentheses, truth table or tautologically equivalent when they have the same truth values on every row of the truth table in the column, oops, sorry about that, bad spelling, in the column under the main connective. And I'm putting main in parentheses in the event that there's a, we're dealing with a sentence that, or sentences that do not have more than one operator. Due to the main operator, okay? So for the sake of reviewing a couple of different examples that, or sorry, rephrase, for the sake of reviewing a couple of equivalences that are really important to us, let me go ahead and throw them on the board. So we've got one De Morgan's equivalence. So sorry, these are I'm going to put De Morgan's equivalences. Examples. Okay, so we can say I have the sentence, it's not the case that both A and B, and then I have the sentence, either it's not A or it's not B. I also have, it's not the case that either one or the other is true, or it's sorry, that was an ugly way of putting it. It's not the case that we have either one of A or B, and that is equivalent to, so both are not. And remember, we just churn out our values. I'll just go through these pretty quickly. We know that the negation on the first pair of sentences, the far left sentence or the leftmost sentence or the left sentence in the first pair is the main connective. So we work the conjunction first. And then we know that the negation rejects each of these. We also know that the way when we have two atomic or simple sentences, we have four possible truth value combinations. So hold on to that, because we'll talk a little bit more about how when you add atomic sentence or simple sentences to the truth table, your number of rows increases exponentially. Then on the right side, We know that it's the disjunction that's the main operator. So that means we work those the values under that last. And in other words, it's the not A, not B that we use to determine the disjunction. So we end up with false, false, true, true, false, true, false, true, and then the disjunction values. By the way, it should be clear that I'm assuming that you know your truth definitions for each of the operators, negation, conjunction, disjunction. And I'm also assuming that you're comfortable with identifying which is the main operator when you have more than one in a sentence. And finally, that you're comfortable with determining the values of the sub operators until you get to all the way up to the main operator. If, however, you have any questions, don't be shy about saying, hey, say that again, or I don't understand, or whatever it might be, right? This is a time for us to do that. I don't want you to feel shy about saying, hold on a second, slow down a little bit. Right? So here, this is one De Morgan's equivalence. We can see that on every row of the truth table, right? In the column under the main connective, the values are the same. So we can substitute out one sentence for another. We are logically saying the same thing when we say not both and either not one or not the other. Okay. Now, for a couple of reasons, that's really useful to us. One reason is kind of, I don't want to say it's a mercenary reason, but it's helpful to us as we're thinking about working through proofs. But another reason is it just helps us to kind of clear up our concepts a bit. So, by the way, I get Zoom is giving me a message saying that my connection is a bit unstable. So if I'm frozen or I've broken up, don't be shy about saying, "Hey Mia, stop! You cut out or whatever." Okay, so the other reason is I mentioned this sort of clarity, right? We get clearer about what we're saying when we use this sort of language, right? So, for example, lots of times people think that not both is equivalent to either not one or not the other, but that's not the case, right? We can, in fact, let's do this. Let's add this sentence. So sometimes people think that not both is equivalent to therefore one or the other, right? So it's equivalent to, and so therefore says one or the other, but all we have to do is throw our truth table out and we see that no, these aren't equivalent, right? They don't say the same thing. Okay, let's go ahead and move down to our second De Morgan's equivalence. Let's go right to left this time. So again, false, true, false, true, false, false, true, true, and then false, 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 true. And then we move over to the other side. True, 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 false. And then, false, 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 true. Right? So you look on every row of the truth table in respectively the negation column and the conjunction column, and we see that these sentences say the same thing. Okay. So, does this ring bells? Is all of this not just familiar to you, but you feel conversant with? What do we think? I hope it's not stunned silence. I hope it's just thoughtful silence. All right, I'm going to move on. Stop me if you have a question. Okay, so now let's talk about a valid argument, right? So a valid argument does not have even one row on which the premises, which I'm abbreviating as PRR, are true and the conclusion is false. Right? So, for example, I think what I'm throwing up here on the whiteboard is an example that we worked last Thursday. I think I then kind of rushed through an example of an invalid argument, but if I didn't, I'll present it here so that we can chat a bit about the difference between the two. So suppose I have as premise 1 the sentence A or B. Premise 2, it's not the case that A, therefore conclusion B. Right? So I say, all right, true, 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 false, 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 true, true. And then remember what we said is the procedure when we have a sentence on a truth table that does not have that does not have an operator. So there's no connective operating on it. We just put the standard reference values underneath that sentence. So in this case, it's true, false, right? So remember, and I haven't written our reference values, but remember that our reference values are as follows. The leftmost sentence takes half true, half false. And then the next sentence over to the right takes half of the first set of values, and in this case alternates. So true, false, true, false. Right now I recognize that we still want to chat a bit about how we generate more rows in a truth table when we have more than 2 simple sentences, and we'll definitely do that. Truth tables can get really long, and as such they can feel really tedious, but it's not bad practice. It's kind of it's good exercise to work them. Okay, so notice then that for premise 1, true. Remember, as long as at least one of the disjuncts is true, the disjunction is true. So A is true, the disjunction is true. A is true, the disjunction is true. A is false on row 3, right? Here it is. A is false on row 3, but that doesn't change the fact that the disjunction is true. Why? Because B is true. The only row on which the disjunction is false is when each of the disjuncts is false, right? We know already that the negation rejects the value of the sentence it's negating. So when A is true, not A is false. When A is false, not A is true. Now let's take a look at the rows on which the conclusion is false, because that's what we need to focus on. if the conclusion is true, we don't have to worry about whether or not the argument is valid. Sorry, I had three sentences that went at once. When the conclusion is true, the issue of invalidity does not arise, right? Remember, an argument is valid provided that you do not have any instance where the conclusion is false while the premises are true, right? So let's look and see if we have such an instance here. Well, on row 2, the conclusion is false, but so also is premise 2. We're good there. On row 4, the conclusion is false, but so also is premise 1. So there is no row on which the conclusion is false while the premises are true. The argument is valid. So what the truth table does when we're talking about truth functionality is to exhibit validity or invalidity. Now, here's a crucial point, everybody. The truth table does not demonstrate or establish or prove the conclusion. It simply shows that the argument is valid. That's why we need a proof system, right, that will use, I'll say that sentence. We need a proof system that uses rules to get us from premises to conclusion. Okay, so we'll say a little bit more about that shortly. We okay with this example? Again, I like using some examples repeatedly precisely because, the more you see it, you remember it, it becomes familiar, right? That said, we'll break out and work different examples together. Okay, now let me show you, again, I don't remember if we worked this last week, but let me show you an invalid argument. And then I want to come back to the concept of validity in relation to a truth table to say a little bit about how the truth table is going to help us make sense of some rules that we'll come up against that we'll learn as we go forward. All right, so first, though, as I said, notice we start with the same first premise, but the difference is that the second premise is an affirmation, not the negation of A, and then here's the conclusion. So this argument lots of times fools us because we often think of the disjunction as exclusive. We say, oh, one or the other, so you can't have both. No, in fact, the truth table shows us specifically the truth definition of the disjunction shows us that a disjunction is true when you have at least one of the disjuncts. So you could have both disjuncts. If you want to assert the exclusive or, you have to explicitly write it out. Otherwise, logic, the truth table says, or is inclusive, right? So when we argue in this way, when we say, well, it's one or the other, and since we have the one, it's not the other, we reason erroneously. So we say, true, 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 false. Here we're just plugging in the values from the reference column for A. So true, true, false, false. And then we're negating B. False, true, false, true. And now let's look at row 1, row 3. Uh-oh. Row 1 reveals that the argument fails. Now, the following is really important. Just because the argument doesn't fail on 3 out of 4 rows doesn't mean that it's okay. The argument is invalid. The rule that is expressed by validity is a rule that is exhaustive. It is categorical. There are no exceptions. The argument fails once. You cannot use it as a rule in a derivation. That's one way to think about it. Okay? It's kind of like saying, look, you lied to me once, I'll never trust you again, ever. And then sticking with it. Okay, so let's push on this idea of how the truth table helps us to see that a valid argument's conclusion is forced, right? What if I do this? So I'm going to just draw a line here so that we don't confuse what we've got. And I'm going to show you, so this argument is valid. This argument is invalid. I'm going to show you what's called an indirect truth table. Okay, and some of you might love it. Some of you might hate it, but I'll refer back to it. Here's how it works. Assume the argument is invalid, which is to say, assume the conclusion is false and the premises, oops, sorry, I didn't finish the sentence, and the premises are true. See if you can generate a contradiction. All right, here we go. I'm going to assume that the conclusion is false and that the premises are true. First, can everybody see that okay? Okay, good. Now we're going to work backward. We did a little bit of this last week, actually, so this shouldn't look entirely unfamiliar to you. So let's go. I'm already on the left side, so let's just work the values. Okay, so what makes a disjunction true? Well, when at least one of the disjuncts is true. So I've been told that B is false, so I'll put that value under there. That means that A has to be true, right? But now, if I put true under A, notice the contradiction I generate. It's a truth functional contradiction. A can't be true if not A is true, right? So when I try to say that the argument fails, I run into a truth functional contradiction. All right, quick question. How many people go, cool? How many people say, wait, what? How many people say cool? Anybody? Bueller? Nobody? Okay, how many people say, ew, this is awful? Okay, Zeba said cool. Okay, thanks, Zeba. I don't know, though, Zeba. Were you doing it just to make me feel better? Does it make sense to say? I love it. Does it make sense to say that when we run into a truth functional contradiction, as we did with not A, right? Does it make sense to say, look, we can't maintain this set of values. It can't be the case that B is false, right? Oh, great, Arshak, great question. I was just going to say, thank you for the transition. I was going to say, you can generate the contradiction where we did with not A, but we could also generate it at the disjunction. Hold tight, let me show you. First, what I want to do is save this whiteboard so that when I do a little bit of erasing, it won't go away, because I don't want too much clutter on the resulting whiteboard. Have I been posting our whiteboard notes, by the way? I think I have, right? Although I can't remember if I did it last week. If I didn't, I'll have to. Yeah, Priscilla, I think you're right. I think I failed to do it last week. So I'll put that on my list. In fact, give me just a sec. Let me write it down, because knowing me, between now and when we're actually done with class, I'll forget. Okay. Okay. So Arshak asks this great question, right? How do you decide which, how do you decide which one is true or false? So now let's do this. Okay, yeah. I'm going to get rid of the green. Okay. And let's start over. Okay, so if not A is true, A must be false. So now I'm going to bring that value under the respective or the other instance of the atomic or simple sentence. And then we said that B is false. So I put the false value under B, and now look, we've generated the contradiction here. A disjunction can't be true if each of the disjuncts is false. And Arshak, have I addressed your question in terms of like when you have options for proceeding, you can generate, if you generate a contradiction, you can kind of do it for the most part wherever you want. There may be more than one way to generate the contradiction. What do we think? Love it? Yes, Mia. I think it's the best ever. Well, let me try this. Okay, now we know what an indirect truth table is. Actually, let me pretty this up. Okay. Here's another indirect truth table. Okay, so A or B, A, so no, oh, sorry, these lines are horrible. A or B, A, so not B. Now we're going to do the same thing again. We're going to assume that not B is false, A is true, and the disjunction is true. And we're going to do the same thing we did before. Let's work backward from those values. If not B is false, B is true. And if B is true, the disjunction is true. Right? So notice what we've done. And by the way, Arshak showing that the argument is invalid, we can do another way. So hold on, rephrase. We can do it another way. So hold on to that. Arshak asks, I get the green part, but why does not B have to be false? Because go back up here to number 1, assume the argument is invalid. In other words, we know that an invalid argument is one in which the conclusion is false while the premises are true. So if we say, okay, I'll assume the argument is invalid. And this is a shorthand way to press for a contradiction. If we don't generate a contradiction and we've done everything right, the argument fails, it is invalid. Yeah, that's what we're doing. We're assuming. Yep. Okay. So let's go at this one more time. Bear with me. I already saved that. Oh, why isn't it? Oh, is that going to save? It might save over. Oh, darn it. It saved over. Crappy McCrapperson. All right. All right. Well, in any event, okay. So I'll just do it here then. A or B. A, not B. Assume not B is false. A is true. The or is true. And now we could do this. We could say, okay, well, I see that A is true. I'm going to go ahead and plug that in. I'm done, because as long as one of the disjuncts is true, the disjunction is true. So we've shown by the indirect method that this argument is invalid. Okay, what do we think? How are we doing? All right, so let me show you really quick before we work on arguments or sentences involving more than two elements, two atomic elements, and what happens when we try to work, let's say, a sentence or an argument that does not have even one truth functional element, right? How the truth table can't cope with that. Okay, so where we're going, oops. Okay, so remember the truth table does not provide a proof for a valid argument's conclusion. So we will need a proof system. 2, the proof system is built out of truth functionality. So let me try to give you a for example. So let's go back to our I'll use P and Q now. Oopsie. Let's go back to what's known as a disjunctive syllogism in some versions of the system. Right? And remember, we know that this argument is valid. When we try to make it invalid, we run into trouble, namely a contradiction. I'm going to piggyback off that in a second. But when we construct the full truth table, we see that there's no row on which the conclusion is false while the premises are true. But let's go back. Let's assume, right, the argument is invalid. When we assume the conclusion is false, when we assume the conclusion is false, we generate or run into a contradiction. That contradiction tells us the assumption is incorrect. That is, that the conclusion is true. So here's where we're going. Here's our first premise. Here's our second premise. And then off to the right, I'm just going to go ahead and throw our conclusion so we know where we're going. We can do this. We can say, oh, I'm going to assume, and P.S. everybody, here's the graphic that we use. We'll use another graphic as well, but when we're working the whiteboard together, almost invariably we will use an indented vertical line to show the start of an assumptive sequence. And then we've got what's known as a little Fitch bar that says, I'm going to assume my conclusion is false, right? Notice I'm not using T's and F's. I'm using the operator to get us there. I'm assuming the conclusion is false. Notice also that my disjunction is one of the premises. And I know that a disjunction is true in 3 ways, right? So since I'm given the disjunction and I don't know what the status is of the truth value, I'm assuming by way of its being a premise that the disjunction is true, but I don't know if P is true, Q is true. I don't know if P is true, Q is false. I don't know if P is false, Q is true. So what I do is I say, I don't know what the situation is, but you know what? I'm just going to go ahead and assume I have P. But look, I've said at line 2 that I don't have P. Here's a contradiction, and we'll learn that in our version of the system, the little hashtag symbol, sorry, my writing's so bad. The hashtag symbol means contradiction. In this case, it's a truth functional contradiction. All right, now I'm going to assume that Q is true. Uh-oh, here again, contradiction. So I've just proven in either case that the assumption that Q is false generates a contradiction. So 3, 4, 5, 6, 7, 8. Therefore, back out on the main line, and sorry, I've reached the bottom of my whiteboard, Q must be the case. Let me erase this and rewrite it so there's more room. Now, you don't need to know all this stuff yet. I'm just telling you where we're headed and give you a sense of how the truth table makes the rules for where we're headed. So hold on just a sec. Let me change. Oh, that is as narrow as it will go. Ah, okay. Sorry, I just tried to do something and screwed up. I'm going to try something and let's see if it works. It might improve your experience of my writing. Okay? Okay. No, I guess that's not going to work. All right, I'll mess about with it outside of class and then come back to you. All right, so P or Q, not P, so Q. I assume that Q is false. I further assume, I'm going to change the color just so that you don't get confused by the indented sequences. I further assume that P is the case, but that contradicts premise 2. I then assume that Q is the case, but that contradicts my assumption. So then I get back out. So 5, 6, 7. I get back out and I say, look, in either case, I generate an assumption. In either case, I generate a contradiction. So it's not the case that not Q, which is to say Q must be true. Okay, so question, Dominic, earlier you said, oh, I'm starting to understand a bit more. Does seeing this example of proving the conclusion as opposed to simply just establishing that the argument is valid, right, is what we're doing on the vertical? What do we think? And you may be digesting, which is totally understandable. Okay, but this is where we're headed. Okay. So before we leave truth functionality, let's just talk a little bit about how we cope with, how we set up a truth table for statements that are that involve more than two simple elements. So compound statements that involve more than two simple statements. So a single simple sentence yields a 2-row truth table every additional simple sentence increases the number exponentially. So here's the formula. So the number, I'll write it out and then we'll put it in more formulaic terms. The number of rows in a truth table is 2 to the power of the number of simple sentences. So we could say, so 2, right, to the power of 2 simple sentences yields 4 rows. 2 to the power of 3 yields 8 rows. 2 to the power of 4, right? 2 times 2 is 4, times 2 is 8, times 2 is 16 rows. So we say 2 times 2 right? 2 times 2 times 2, 2 times 2 times 2 times 2, and so forth, right? So suppose we have, the following animal. We have the sentence, It's not the case that A, or it's both B and C. So we have 3 A, B, C simple or atomic sentences, which means we have 8 rows. And then here's the conventional approach. You use it all the time. Every single time you set up a truth table, you do the following. Working left to right, you take half the total number of rows, in this case 8, and you get 4 true, 4 false. Then you take, for the second atomic or simple sentence, you take half of the first sentence's truth values, right? And you divide, so 4, you divide those in half and you write true, true, false, false, true, true, right, and so forth. So since there are 4 rows, you get 2 true, 2 false, 2 true, 2 false. Then the last sentence, and this is always the case, however many simple or atomic sentences you have, your very last sentence, the sentence on the far right, is always going to alternate true, false, true, false, true, false, true, false. Right? So notice here, though, you've got 3 simple sentences. So you take half of B's values and you divvy that in half in terms of T's and F's. So true, false, true, false, true, false, true, false. And then you proceed accordingly. Now, how do I know that A, B, and C go in that order in terms of left to right? Well, we're just reading according to standard English left to right. Okay. So this is the convention that's adopted. Pick up any logic book and this is what you'll see. Always laid out this way. Half true, half false. And then keep having, H-A-L-V-I-N-G, keep having it. So what we end up with is this. We know that the disjunction is the main operator, so going left to right, I'll work the negation first, then I'll work the conjunction, then I'll work the disjunction, right? So I say false, 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 true, 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 true. Conjunction, B and C. So look at those reference values. We get true, false, 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 true, false, false, false. And then we're taking the values under disjunction, or the values under negation, the values under conjunction, and by the truth definitions of the disjunction, you get true, false, 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 true, 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 true. Assuming that I've done everything right. As you can see, the rows get a little bit wonky, right? So assuming I've done everything right, those are the possible values, the conditions under which the disjunction is true, the conditions under which the disjunction is false, given these elements. Okay. All right, what do we think? How are we doing? And thank you, Dominic, for clarifying. Yeah, so the indirect truth table. Yeah. We can go ahead and work a couple more because one of the, contradiction is a crucial concept for us here. But before we do that, first, are we okay with the approach to, the standard approach to generating a truth table? Yay. And think about it this way, right? This is a machine, right? that we're using to grind out truth values. I sometimes, I think about, a sort of one of those what are they called? I can't think of what they're called now. Ugh. Anyway. Okay. All right. So I'd like us to push more on 2 ideas, right? So I mentioned already working the truth table for validity, but also I want us to wrap our heads even more around what the truth table does by considering an argument that we know is valid, but it's not truth functional, and so it's going to fail on a truth table. Okay? All right, so suppose I have the following sentence. I say A is identical to B, B is identical to C, therefore, so premise 1, premise 2, conclusion, so A is identical to C. Right? You know and I know that this is a valid piece of reasoning, but it's not in the truth functional logic system. It's in a system that encompasses truth functionality, but it's not itself truth functional. Well, what do I mean by that? Well, let's throw each of these sentences into a truth table. Where we've got a premise. Oh, you know what? Let me push it down just a little bit. No, I guess I can make it work. Premise 1, premise 2, and the conclusion. Now, the identity symbol is not a logical operator a la negation, conjunction, disjunction, right? It does not operate, it does not have a truth function. So we'd say, okay, this sentence is either true or false, right? And remember, we've got 3 sentences, right? So 8 rows, true, 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 false, 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 false. Take half of that. True, true, false, false. True, true, false, false. And then finally we take half of that. True, false, true, false, true, false, true, false. All right. Let's look on every row on which the conclusion is false. Here, 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 here. So rows 2, 4, 6, and 8. But check this out. So the truth table tells us the argument is invalid, right? So the truth table is not the right mechanism let me rephrase that. It's not the right tool. It does not have the right mechanism to determine the validity of this argument. Right? I mean, one way to think about what's going on here is in terms of, using a blood pressure cuff to test somebody's temperature. Like, you don't do that. You don't test somebody's blood pressure, you don't test somebody's temperature, or take somebody's temperature with a blood pressure cuff, right? Or suppose that, someone has an all battery car, right? You don't walk with gas and say, okay, open up that battery. I'm going to pour some gas in. No, it's not the right, the car won't run that way. So what we want to understand is that the truth table is incredibly robust and precise, but its scope is limited to truth functional connectives. Right now, those are negation, conjunction, disjunction. Okay. It's also the case that we can take the meaning of a term and kind of misuse it, and the truth table doesn't won't care. So here's an example. Suppose I have the following sentence. Walter is a dog. And I have the next sentence, Walter is a cat, right? And since, remember, you don't use the same capital letter for two different sentences, I'll use capital D to represent the sentence, Walter is a dog, and I'll use C to represent the sentence, Walter is a cat, right? Now, so Walter is a dog, Walter is a cat. True, true, false, false, true, false, true, false. You see where I'm going with this, right? There's no possible way that Walter can be a dog cat. And yet, hello, row number 1. All right, so the truth table does not care about, it's not, I'm borrowing from another logic text. It's not sensitive to term meanings, word meanings, right? So, when we're using a truth table, all we're doing is taking possible truth values and, right, by way of truth definitions, grinding out the possible values of compound sentences. Okay, so the truth table is not sensitive to meaning or context. So, if you want to use the truth table to work with sentences in specific ways, you need to make sure your translation, acts accordingly. All right, so finally, and then on Thursday, I promise we'll start applying the work we've been doing to derivation rules. It's going to be loads of fun. You're going to have the best time ever. But let's do a little bit more work on setting up a truth table and constructing and completing a truth table to test an argument for validity. So how about this? Let's take the following. And by the way, question for you. I know Priscilla says yes to doing more work on validity. Do you mean, Priscilla, specifically an indirect truth table, a complete truth table, or both?
Both, yeah.
If I'm not mistaken, as a quick note, our textbook does not ask us to work with the indirect truth table. That's just something that I push really hard so that when we get to understanding what a logical contradiction is in the context of a derivation, we have recourse to the indirect truth table. So don't feel like, oh crap, I need to know how to do this. You don't. It's just nice I think it could be nice for you if you do. Okay, so how about this argument? Let's say we've got the following. Not both A and B. It is B, so it's not A. All right, so first, we've got to complete the subconnective values for the conjunction. Then we work the negation. There are no values to work for B. It's a simple sentence, right? So there's no connective operating. So we just work the values for B, and then we work values for not A. So I'm going to assume the following: premise 1, premise 2, conclusion. Okay. So true, false, 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 and then false, true, true, true. Scribble these out so they don't distract me. True, false, true, false. And then finally, false, false, true, true. So we need to look at the first two rows because those are the rows on which the conclusion is false. Sorry, my connection is lagging a bit. So the arrows I'm drawing in front of to the right of the F are, each F's are coming up slowly. Okay, so in sentence 1, the conclusion is false, but so also is the first premise, so no worries there. In row 2, the conclusion is false. Sorry, everybody. Can you see and hear me okay? Or can you see the whiteboard more importantly? Okay, sorry about that. Where I was yapping away and then I got disconnected. Where were we? Where was I? Do you mind? Had we got through row number 1 yet? I'll start over just in case. So row number 1 has a false conclusion, but here's my check mark. The first premise is false. So no contradiction, so there's no problem having a false conclusion, right? Remember, the only scenario that cannot obtain if you're claiming you have a valid argument is true premises and a false conclusion. So since our first premise is false, no big deal. Second row, false conclusion, but check out premise 2, that's false. So the argument is valid. What do we think?
Wait, can you repeat that again? So the first one is, I don't know. Can you just repeat it again?
Sure. So on row number 1, the conclusion is false, but we do not have a case in which both premises are true. If both premises were true and the conclusion were false, the argument would be invalid. I know you might be feeling like you're playing a bit of mental twister. I get it, right? But there's no row on which the premises are true while the conclusion is false. So that's why I put a check mark next to the F on premise 1 and the F on premise 2.
Got it. Thank you.
Yeah, no problem. And I know this can be, a bit. Yeah, what do you think, Arshak?
Is the argument valid because in the third row everything is true?
Great question. No, the argument is valid because there's no row on which the premises are true and the conclusion is false. We want row 3. We love row 3. That's, that if that world obtains, that means that the argument is sound. But go back, remember, hey kid, I have candy in one hand or the other. It's not in the one hand, so ha ha ha. What row is that? That's row 1. Hey kid, candy's in one hand or the other. It turns out that that's actually false, right? The argument is valid even though one of the premises is false. It's not valid because all the premises on row 3 happen to be true. That's a great question, but yeah, you gotta think about sort of juggling truth values. Okay, so we're just coming up at time, and I want to make sure that you have questions, problems, confusions addressed. I'll keep this whiteboard, and we'll pick up with this on Thursday, and we'll work. We're going to start working on derivation rules. Victoria, what are you thinking?
I just wanted to ask, may I use another logic, like I just look about to, I think it's valid.
So I apologize, Victoria.
Because it's truth, because it's not false.
So I apologize, Victoria. My connection seems to be unstable. So the audio is not coming through very clearly.
Okay.
Could you try one more time? Do you mind repeating what you said?
Okay. Okay. Maybe next time it will be better.
Okay, I'm sorry. So do me a huge favor if you can. So hold on. I'm gonna say something in the chat.
If it's difficult for right now, maybe next time
So
it will be better.
email. Oh. Hi everybody. Can you hear me? I'm using cell data. I'm hoping that it works. And I know we're at time. Okay, thanks, Arshak. But let's see. So Victoria, so I apologize. Victoria, do me a huge favor, and if you would, go ahead and send me an email with your question, and I promise we will pick it up. I'll respond to your email, but we'll pick it up on Thursday. Alternatively, if you want to just wait until Thursday, that's fine too, but I apologize. Okay. Thanks, everybody.